Okay, we're going to be looking at two examples because they're very, very short in section 8.1 of chapter 8. So we are looking at pressure vessels, and we want to remember that with pressure vessels, if we have a cylinder, so it's going to be something that is shaped like this, then as I look at this, I'm going to have my hoop stress, and it's just like a hoop that goes around like a whiskey barrel. And I'm going to have that longitudinal stress. So we have hoop stress and longitudinal stress. And our hoop stress is PR over T. That longitudinal stress is PR over 2T. Now, if I have a circular pressure vessel, it is the most efficient shape that we could have. And so all of these are going to be like my stress 2 because it is half as much as stress 1. And so we will only be looking at PR over 2T. So that's just something that's important to keep in mind. So we have a pressurized spherical tank, which is made of 0.5-inch thick steel. If it is subjected to an internal pressure of 200 psi, determine its outer radius if the maximum normal stress is not to exceed 15 ksi. So I have that my maximum normal stress is 15 ksi, and that's what allowed. And it is made of, so I have a thickness of 0.5 inches. It has an internal pressure of 200 psi. So this is ksi, this is psi. So let's just go ahead and put this to 0.200 ksi. Okay. And let's see, if it is made of blah, 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 determine the outer radius if the maximum normal stress is not to exceed. Well, something that we need to keep in mind is when we're looking at these equations, like what is the internal or what does the radius mean, okay? And this radius in the equation, this is my inner radius. It's always the inner radius, okay? And so my equation, inner radius, PR over 2T, this is going to be my inner radius. So if I want to know the outer radius, then I have to understand that my outer radius is equal to my inner radius plus my thickness, okay? So we've gotten everything defined, and I have 15 ksi, so kips per inch squared equals pressure 0.2 ksi times inner radius, I don't know that one yet, times 2 times my thickness. And now if I work this out, I'm going to take 15 and I'm going to multiply times 2 times 0.5 divided by 0.2. I get an inner radius of 75 inches. So if I want that outer radius, it's going to be 75 inches plus 1/2 inch equals 75 point, whoops, I said 75 and then just made it 7.5, equals 75.5 inches. So that is the outer radius, okay? So then the next problem we're going to do, I want to talk about, you need to really like read through a problem and understand what's happening. We have a thin-walled cylinder. So when I have a cylinder, it's going to go back to the pressure vessel over here, where I have a sigma 1, which is my hoop, and sigma 2, which is my longitudinal. It can be supported in one of two ways shown. Determine the state of stress in the wall of the cylinder for both cases if the piston P causes an internal pressure to be 65 psi. The wall has a thickness of 0.25 inches and the inner diameter of the cylinder is 8 inches. So before we get started, we want to find the stress created in the wall. And we have an internal pressure of 65 psi, pound per inch squared. We have a wall thickness of 0.25 inches, and we have an inner diameter of 8 inches. So our radius inner is 4 inches. And because we have a cylinder, we're going to have both sigma 1, which is hoop, PR over T, and sigma 2, PR over 2T. And this is the hoop, and this is longitudinal. Okay, in this case, as I'm pushing down, there is pressure being created. It is going to want to push out, which is going to create a hoop stress. However, these walls are not taking the longitudinal pressure, the force pushing down on this, the liquid is pushing back up. And so the pressure in the longitudinal direction of the tank is 0. When I look over here, all of a sudden, as I am pushing down, we are creating pressure in here and it's going to be pushing out. So that's our hoop stress. But we are now putting a force in the sidewalls. Okay, putting a force in the sidewalls of this because it's being connected. So if I'm looking at reactions here, it's all internal. Here, we are creating reactions where we're hanging, which means we have to have a longitudinal stress in the wall that's coming. So here, we're going to have hoop stress, PR over T. Our longitudinal stress is going to be 0, again, because we're pushing back equal and opposite. There's nothing going on here. Over here, we're going to have a hoop stress, but we are also going to have that longitudinal stress, which is creating the reactions in the wall. Okay, so let's look at stress 1. So we have our pressure, 65 pounds per inch squared, times our inner radius, 4 inches, divided by our thickness, 0.25 inches. So stress 1 equals 65 equals 1.04 KSI. So I got a really large number on my calculator when I did that. 65 enter, 4 times 0.25 divide. 65 enter, 4 times 0.25 divided by. We get this very, very large number, which is in PSI. So we're just going to go 1, 2, 3 and call it 1.04 KSI. And again, stress 2 equals 0 because it's the actual plunger pushing back. Over here, stress 1 equals, well, we still have the same pressure, 65 pound per inch squared. We still have the same inner radius, and we still have the same thickness. So sigma 1 is still going to be 1.04 KSI, but we've introduced that longitudinal. So we have 65 pound per inch squared times 4 inches divided by 2 times our thickness. So I get 65 enter 4 times 2 divided by 0.25 divided by, and because I have this one in KSI, we're going to make 0.52 KSI. And there we have a solution for both these two situations. So make sure when you're reading through your problems, you understand the statics. What is our equilibrium point?